Good morning. Happy Independence Day to all Indians. So, welcome to Krishna's class. We shall look at the parallelogram law and how it manifests in the case of the inner product. Recall that in every parallelogram, some of the squares of the diagonals, of the length of the diagonals, is equal to sum of the squares of the sides, squares of the length of the sides. This is parallelogram now. So it means the following. Suppose you have a parallelogram. Which is a plain geometric figure with O, A, B, C. Then OC is the diagonal, AB is another diagonal. So what the theorem says is this. I mean, this is a very classical theorem in pure geometry. One can prove that. I put bar here to show that OC square plus the distance AB square equal to the length OA square plus twice length OA square plus twice length of OB square. This means actually the length of OA square, length of OB square plus length of BC square plus length of AC square. Now you know that in a parallelogram, the length of AC is the same as length of OB, length of OA is the same as length of BC. Therefore, we get twice length of OA square plus twice length of OB square. Now this is the parallelogram. This is the classical parallelogram law in pure geometry, which you can prove with the help of Pythagoras theorem by doing some constructions and so on. Now what you have here, you know that you can look at, consider the space R2 over R with the usual inner product or what you call dot product. Usual dot product. This is an inner product space. Then if U and V are vectors in R2, U and V are vectors in R2, then the length of, see, U plus V and U minus V are vectors with the property that norm which is the length of U plus V, that is a diagonal, or I will put it this way. I'll put it this way, that U plus V and U minus V with the property that U plus V is a diagonal vector and U minus V is a translate of the other diagonal. I'll put it this way. So in R2, we take two vectors U, this is U, this is V, then this is your O, correspond to OA, this corresponds to OB. Now you know how vector addition takes place. It is through parallelogram now. So U plus V is the vector which is the sum of the two vectors U and V given by the diagonal OC of the parallelogram, because addition takes place using parallelogram. And U minus V is actually the following. This is minus V. This is vector. This is U minus V. This is U minus V. Okay, this is minus V. This is minus V. And this is U minus V. Now you see that the length of OD is equal to the length of the diagonal AB of the parallelogram. Length of the parallelogram. That is which is law of movements. See this length OD is the length OD is equal to length of AB. Okay. So as such, OD is the vector u minus v. That's why I have drawn here. I have been very careful in making a statement about u minus v. Okay. Therefore, what one gets is the parallelogram loss is square. Now this is the expression of one of this particular thing translated to vectors in R. So we can generalize it. And you see that here U defines therefore this can be expressed in the form of inner product of U plus V with itself, U minus V with itself, this one inner product of U minus V with itself, this is again inner product of U with U, this is inner product of V with V. Okay. So that's very easy to see in R2. And now we can take up a Hilbert space or an inner product space. So now consider, so let H tilde that means H tilde is not necessarily H tilde closure is a Hilbert space. So we are just distinguishing the notations using H and H tilde. So H tilde closure is the Hilbert space H. That's our usual notation for Hilbert space. Okay, that is so we shall work in H tilde. So H tilde, let denote the inner product in H tilde. Then for any U belonging to H tilde, norm of U square equal to inner product of and the parallelogram law, one can prove that still the U plus V this is quite simple. This is quite simple. All that you need to do is just compute this U plus V whole square and U minus V whole square. Now, so you see that similarly similar representations for U minus V whole square so let us take the left hand side. So norm of whole square, this is equal to if you expand it using the properties of the inner product, this turns out to be plus this part, namely UU minus EU plus, and here you see that there is some cancellation taking place. They cancel, and so you get this is equal to, now that proves this theorem. Okay, thus parallelogram law holds good in any inner product. That's the conclusion. Thus, parallelogram law holds good in any inner product space. Now, having proved this, you ask the following question: is it valid in any normed space? This is the question that you ask. If it is so, then it has nothing to do with inner product. Otherwise, it has something to do with inner product, although we have used the inner product to prove this result. Okay, so that's the question that we ask. Right? We'll take an example. So let us take we shall take R2 with norm 1. Okay, where norm 1 equal to mod U1 plus mod U2, where U is given having components U1, U2. So this is a normally linear space. You should use the short notation here, non-linear. So this is a non-linear space. Okay, so R2 linear space. I mean, that's something that you can easily prove. Okay, satisfies all the conditions to be satisfied by a norm. Now let us show that this parallelogram law fails to hold, parallelogram law fails to hold in R2 with no. Okay. So consider where x is given by the vector 2, 1. Or you can use u. 2, 1. And v now it's quite easy to compute. Norm 1 equal to 3. Norm is also equal to 3. So you see that it is actually mod 2 plus mod 1 is 2 plus 1, that is 3, and mod 1 plus mod 2, that is norm 1 is equal to 3. Okay. Now norm of x plus y or norm of u plus v 1 equal to what? What is u plus v? U equal to 2, 1, v equal to 1, 2. So you just add it, I mean component wise. So you get this is norm of 3, 3, 1. Norm of 3, 3, 1. And that's equal to 6. Norm of equal to u minus v is what? U minus v. This is actually 1 and minus 1. This is equal to 1. Okay. Now of u minus v. Therefore, let us now compute. So norm of this is equal to 6 square plus 2 square 40. Norm of u square, solve 1 now. U square equal to this is equal to 3 square plus 3 square, that is 18. Okay. Now twice this is equal to 36. And is not equal to square. That is, the parallelogram law does not hold in Thus the parallelogram now hold in this non-linear space. And note that is now 1 is not a consequence of any other. Of course, you might ask the question, do you have another inner product on the space from which now 1 can be derived? Okay. So, we shall address this question. Okay. Right. So, that's a question that can arise. But in R2, is an inner product space and the parallelogram is good. So you might ask the next question. Could it be that norm 1 is derivable from some inner product different from the we shall address this question. And it leads to, addressing this question leads to a very deep characterization. Nice characterization. Here are of inner product spaces. Okay, let us explore this. I am not going to give the proof of the main theorem, but I'll just tell you exactly how it's working. It's a very important theorem proved by great mathematicians like Kollam and Jordan. And there is one more author whose name I don't remember now. I couldn't get the reference also immediately because the book is not with me right now. Otherwise, see, it is all in the Yoshida. Okay. Now, let me prepare the ground for addressing this question. So, definition. To define what is called a free Hilbert space. Change the title. Definition of what is called a free Hilbert space. A non-linear space. A non-linear space is a free Hilbert space called a free Hilbert space is called a free Hilbert space if the norm satisfies the parallelogram. Okay, so this, we'll put it this way, norm the linear space plus parallelogram. Equal to free Hilbert space. It's just one step short of becoming a Hilbert space. So all that you need is complete the space, then you get a Hilbert space. Okay, so that's one definition. And of course, inner product space you already. And likewise, an inner product space a linear space over R of C with an inner product. So linear space plus, so it's linear space plus inner product. This is what you call inner product space. So we have now two terminologies. One is the pre-Hilbert space and the other one is inner product space. There are two terminologies. Are they the same? Okay. If they are the same, then of course it addresses this question, that is, no normed linear space where the norm does not come from an inner product can be a pre-Hilbert space. Okay. So one of the fascinating results in this direction is the following. This is the main theorem, which is due to von Neumann. H is what? Say, pre-Hilbert space if and only if it is a so they are one and the same. Okay, every inner product space is a pre-Hilbert space, and every pre-Hilbert space is a inner product space. Now you see, we have already shown that through some remarks. I am not going to give a proof. For proof of this theorem, refer to A. Yoshida, function. This is Springer book. This theorem is proved by online. Jordan and so it's not a theorem that has been proved by any ordinary mathematicians. This has been proved by two great mathematicians or three great mathematicians. One more author is there, which I don't anyway. Because unfortunately, I don't have this in my hand right now. I could not get the information. But if I get it, I will just tell you what it's later. Okay. Now, so what have we proved? We have already proved that every inner product space is a pre-Hilbert space. Why? Because if you take an inner product space, there is already a norm. Okay, coming from the inner product, and the parallelogram law holds good. Therefore, any normed linear space with a parallelogram law is a pre-Hilbert space. So, this is relatively the simple part of it. Okay. The converse is rather difficult to prove. One has to show that a pre-Hilbert space a normed linear space satisfying the parallelogram law. So that makes it a pre-Hilbert space. Has the property that the norm is derivable from some inner product. So for the details of the proof, please look into Yoshida. Okay, that is, one has to show that the norm is derivable an inner product defined using the norm. So one has to set an inner product or a dot product and then verify that it has got all the properties of the inner product, and that inner product has to be defined using the norm. Okay, so in terms of the norm you have to derive. So the inner product of x with y has to be expressed in terms of the norm. Okay, you can use the norm of x plus y, norm of x minus y, norm of x plus iy, norm of x minus iy. All these things are used in the expression. So since I am not going to deal with the proof, I am not going into the expression. So you can get all the details in the marvelous book on functional analysis by K. Yoshida, which is a classical function. One should necessarily have a look at it. And it is packed with a lot of information. And such beautiful theorems are proved. So I leave the proof and the details for you to look into Yoshida. So let me, like here, thus the property satisfies the parallelogram. Is a characterizing property of inner product spaces. So H tilde with an inner product is an inner product space. If H tilde is a normally linear space where the norm satisfies the parallelogram law, then you call it a pre-Hilbert space. So a pre-Hilbert space is an inner product space, and this gives the proof of this theorem. So this part is I should warn you that is you have to actually define the inner product using the norm, and then prove that whatever you have defined has all the characteristic features of n. So it needs some work. So I am not taking it up, but I think one of the earlier lectures on Hilbert spaces in this series, in my series, actually you refer to the series of lectures earlier. If my memory is right, I think I have proved it there. Okay. So with this, I conclude today's lecture, and thank you very much.